So for a problem like example A here, p of x equals x to the fourth plus 9x squared, the goal is to find all the roots. I would start by factoring this. You can factor out the x squared that leaves behind x squared plus 9. It's nice to have things factored because you can do a divide and conquer approach. So if you have something factored, something times something else, when you try and solve for this equals 0, its roots, its x-intercepts, then either x squared equals 0 or x squared plus 9 equals 0. Now that's only one solution here, x equals 0, but it's a root of multiplicity 2. On the other hand, x squared plus 9 gives you x squared equals negative 9, x equals plus or minus the square root of negative 9. How does the square root of negative 9 simplify? 3i. Perfect. Thank you so much. So those are all my roots. Now you could be asked to give the linear factorization of this. If you were, then let's take a quick look here. We've got roots and binomials. The root is at x equals 0. That's just a binomial of x. But for a root at x equals 3i, the corresponding binomial is x minus 3i. Moving that to the other side changes its sign. Yes? Am I not sharing my screen? Oh, there we go. Sorry about that. Let me keep going. We've got a root at negative 3i, x equals negative 3i. If I move that to the other side, then I get x plus 3i. That's another binomial. I can put these together along with the multiplicity there and come up with my factorization. P of x is x squared, because remember there's two roots of 0, and then x minus 3i and x plus 3i. So that's the linear factorization, or excuse me, that's the factorization of p of x. And along the way, we also found the roots. So nice. In section 3.5, you're going to start getting lots of imaginary or complex roots. Let's see that again with example B. Let me take kind of a quick look at example A here. I'm not sure if I got that one graphed or not. Let me take a look back here. Yeah, there it is. So you see classic behavior of an even degree polynomial with a positive leading coefficient. So both ends point up. Okay, not a big surprise there. But when you look at the graph closely, you only see it touch the x-axis at one place, at 0. That's a bound, so it has multiplicity 2. But what that's saying is because there's a degree 4 polynomial, and we can only see or account for 2 real roots, the other 2 have to be complex roots or imaginary roots. So kind of a long explanation for a short amount of gain, but it is worth knowing. Let's see if we can apply that to example B here. So for example B, we've got p of x is x to the third minus 4x squared plus 13x. And like the last one, I'm going to start by factoring out the x. This time I only can factor out 1x. That's okay. But when I set this equal to 0 and solve, so if I set p of x equal to 0, then again, it's a divide and conquer approach. I either get x equals 0 or x squared minus 4x plus 13 equals 0. And this one won't factor. Now I know that because I expect complex roots. You're not going to get something to factor if it has complex roots. How is that going to solve? Well, we're going to use the quadratic formula here. It's not really written, but it's understood that a is 1, B is negative 4, and C is 13. Now, particularly when you have a negative value for B, I highly recommend that you write your quadratic formula, and I'll spare you singing this to the tune of Pop the Weasel, Pop Goes the Weasel. Write your quadratic formula with parentheses. So it's the negative of negative 4. Really easy to miss that double negative unless you're being careful with the parentheses. Negative 4 squared should give you positive 16, not negative 16. Again, a mistake you're going to make without the parentheses. Times, or minus 4 times A, which is 1, times C, which is 13, over 2 times 1. Lots of simplification here. 4 plus or minus the square root of 16 minus 52 over 2. And there's some interesting wishful thinking that happens quite often with this problem. I'll get 4 plus or minus the square root of 36 from a lot of students. And that's close, but you're missing one important element. What is it?
The negative?
The negative. Well done. Thank you, Kyle. So that's going to be 4 plus or minus 6i over 2. Don't just cancel one of these into the denominator. You've got to view this numerator as one whole term, and you can't cancel into that binomial. I can factor out a 2, and then parentheses. That leaves behind 2 plus or minus 3i over 2. And now the 2's cancel. So you get 2 plus or minus 3i. So those are the other two roots for this polynomial. Now to kind of backtrack that a little bit and look at the roots. And the corresponding binomial, it's going to look like this. We had a root at 0, so the binomial there I'm just going to write as an x. And I had a root at x equal 2 plus 3i, and a root at 2 minus 3i. Now I'm going to regard these as kind of one whole term. I'll give you a couple options. But if I play my usual game, kind of like I did back here when I moved the 3i to the other side and the negative 3i to the other side to get the binomials, if I play my usual game, then it's going to look like this. X minus, remember, because it's going to change signs, 2 plus 3i equals 0. And then x minus 2 minus 3i, again, equals 0. And I regard this as one whole binomial and this as another binomial. So if you want to keep it from getting too messy, just write it like this. P of x is x times this one, x minus 2 plus 3i. And then I'll put the parentheses around that. And then another set of pink parentheses. Oh, rats. Juggling too many markers here. How about that? And then x minus 2 minus 3i. Let's put in some proper notation here for us. Starting with a minus here, like that. Now there's nothing wrong with leaving it like this. I actually kind of like that. Some people prefer to do it like this. They'll distribute that negative sign and get x minus 2 minus 3i and x minus 2 plus 3i. And that would be your binomial. You could use either one of these here. But notice you've got an x times an x times an x. That's your cubic polynomial. All right? So this is the complete factorization of that polynomial. Whew, that's a little bit of a tricky one. So are we okay there?
May I ask a question?
Yeah, please do.
Why did you, so like, when it's x equals 2 plus 3i, you need to set it to 0? So you move the whole thing?
Yeah, I moved the whole thing. I could have moved it one at a time. So if I move the 2 over, it becomes -2, and the 3i becomes -3i, and I'd get this binomial. I just picked the whole piece up and moved it over en masse, and it gave me this.
All right.
So it's just a matter of preference, Kyle. I mean, on a test, if you gave me this or x times x minus 2 minus 3i and x minus 2 plus 3i, either one of them is correct. There's no real preference for one or the other. It's just whatever you're comfortable with, okay?
Okay.
All right. Okay, so there's one last one that we got to take a look at, and I'm going to kind of make short work of this. I am going to show you or remind you of a little trick. So before we do example C, I want you to recall a couple things, and that is if I had a cubed plus b cubed or a cubed minus b cubed. Both of these things factor. I have an a and a b, and then you multiply this term by itself, a squared, this term by itself, that gets you the n terms. The middle term is just this times this, a times b. And I'm not putting in the signs just yet. Let's do the same thing down here. It's always a binomial times a trinomial. So it's going to be an a and a b, the things you cube to get these. This term times itself, this term times itself, and then this times this, ab. Somebody who had me last semester, remind me, what's the word I use to help me remember and fill in the signs?
Soap?
Yay, thank you. Soap, soap, soap. Same sign, opposite sign, always positive. So these two signs are the same, plus and a plus. These are opposite, plus and a minus. Minus there. And the last one is always positive. Same sign, opposite sign, always positive. So we're going to need that in the problem that comes up. And that's going to be our last one, example C. I'm going to solve part of this. It's a long problem that's in your homework, and I'm going to solve 70% of it for you, maybe a little bit more, 80%. X to the 6th minus 7x cubed minus 8. Whew. All right. Well, if that's my p of x, and I've made a lot of gains in these types of problems by factoring it, I'm going to see if I can't factor this. But here's the thing. It just, you got a 6th power, you got a 3rd power. It just doesn't look all that easy to factor. But if you take a look, you'll notice that the degree of this exponent is half of the degree of this one. And that makes it quadratic in form. So let me write it like this. I'm going to write it as if it was a quadratic equation. Now, in doing that, I'm really making a little substitution. I'm saying, all right, you know what? I'm going to let u take the place of x cubed. And then when I square x cubed, I'll get x to the 6th. So this all lines up pretty nice. But maybe now we can factor this. Let's factor the easier problem. That's going to be a u and a u. How's this going to factor?
Oh.
Minus 8.
U plus 1?
And plus 1. Beautiful. That's how this factored. Now, how can I use that to factor this? Well, what was u taking the place of? U was equaling x cubed, right? So that means this is x cubed minus 8 and x cubed plus 1. Ah, okay. So that's our factorization of p of x. If I want to set this equal to 0 and solve, what I'm going to notice for you is that this first term is the difference of cubes. So the difference of cubes is always going to be a binomial times a trinomial. And I'll tell you what, this trinomial will not factor. In fact, it's going to have complex roots when you finish solving it. And then this one is going to be the sum of cubes. So it's going to be a binomial times a trinomial again. Now I'll help you out with the first one. Let's see, what do you cube to get each of these? An x and a 2. And then x times x is x squared, 2 times 2 is 4, 2 times x is 2x. Same sign, opposite sign, always positive. Minus, plus, plus. This next term is the sum of cubes, and I'll help you out a little bit with that one as well. So the only thing I'm not telling you is how this last term lines up, but you can spend a little time with your factorization of the sum of cubes and get that one. We can read off some of the solutions here now. That first one is x equal 2. What's this one? That's x equal -1. That's a solution. And this one,
Is that
you're gonna have
x
to,
plus 2 squared?
no, it's close. If that was a 4x, it'd be x plus 2 squared. But this won't ever factor for you. So it's close. It's x plus 2 squared would be x squared plus 4x plus 4. We've got a 2x there. So what you're going to have to do is you're going to have to solve that x squared plus 2x plus 4 equals 0 with the quadratic formula. And I'm not going to spend the time to do that here. Suffice it to say that you can solve that, and what you'll end up with is x equals -1 plus or minus I times the square root of 3. Or you can write it as 3 times the square root of 3 times I. The only reason I don't write it like square root of 3 times I very often is because that I tends to get slid underneath the radical. And we're not going to take the square root of I until we get to trig. So, yeah. In any case, so there's 4 of your solutions. 1, 2, 3, and 4. What you've got to solve is this right here. If you actually looked at the polynomial, looked at its graph, and I think I've got that up here, I can see 2 real roots at -1 and 2. Since this is a 6-degree polynomial, that means the remaining 4 roots have to be complex. So what I'm saying is that these last 2 you should expect to be complex. Whew. All right. A lot of work there, but I got you most of the way done with this problem, so it should be good. Any questions or thoughts on that? All right, cool. Let me stop things here and let you finish up.